Yes, so hello Faiza, hello Madiha, Assalamu alaikum. And Madiha, after so many years you are joining.
Yeah, sir,
Yeah.
I left for a month, sir.
Oh. Are you all right? Everything good?
Yes, sir. So I had my half yearlies plus like I wanted to take a break. My vacation
Oh,
started. Yeah.
okay. So you reached some saturation point and then you wanted to just, yeah, get away with these. Good.
Uh,
Okay, so yeah, it's good that we are starting some new chapter. So it's good.
all right.
Okay, but yeah. Yeah, so this was the homework in the previous class, right, guys? So did you guys again? You guys didn't miss. They didn't send me the homework. Tarif, Faiza, and
Sir, I have
Fabis.
sent it.
Oh, you have sent me.
Yes, sir.
Oh, but I didn't get any. Okay, sorry about that. So I will. Yeah, I will ask the Learnivio team. Maybe they have missed. Okay, so yeah. So let me again do one more question, which was based on this. So which is based on this solid angle, right? So let's say that in the previous question we solved the electric flux. So the charge was placed at this place, right, at the apex of this cone, and we calculated the electric flux through this base, right? So we calculated the electric flux through this base, which was circular. So in this base, right, the electric field lines are crossing, and then we calculated the electric flux, which was how much? So for 4 pi, it was q by epsilon naught, right? And then we calculated the conical angle. So this angle was how much? This angle was theta, right? So this was, anybody remember? Does anybody remember?
Alpha.
Yeah, so that is why I am saying that you guys keep revising. So 2 pi 1 minus cos theta, right? So this would be q into 2 pi 1 minus cos theta by 4 pi epsilon naught. So this would be simply due to this cone on this surface, the flux would be q by 2 pi epsilon naught 1 minus cos theta, where theta is the angle in radian on this from this slant height, right? So this question we did, right, guys?
Yes, sir.
Yeah, so I found one more question, and so I wanted to repeat that question. So that was yeah, that was again a very beautiful question that I wanted to.
Sir, can you scroll up?
Oh, so this you have noted earlier, right, Tariq? This we discussed in the previous class. Sorry,
Oh, yeah.
yeah, sorry, Madiha, you won't be able to so collect this part, but shortly we'll start the next chapter. Then you would be able to connect with us. Okay,
Yes, sir.
okay. Sorry about that. I need to repeat, and then I'll come to the second chapter. Okay, so we have a similar kind of question. In this question, we have a hemisphere, right? And on top of a hemisphere, a charge is kept. Q charge is kept, and they want us to calculate what would be the electric flux through this area, through this base. So you guys, can you guys figure out how can we use the solid angle property? Yes. Because if you want to calculate the flux doing the integral, then it would be, so if you want to calculate, this would be E dot dA, and this is not a closed surface, this is an open surface, so this would be not closed integral but integral, right? And then you need to figure out that let's say this is d theta angle, and this is ring, right? And then this is dr. So there'll be more difficulty in solving this problem to calculate the whole integral. But when you know the conical property, but when you know the conical property, that would be easier. So you can calculate in just 3 or 4 steps. Yeah. Any idea, guys? Tarif, Chavez, Faiza, any idea? We need to calculate flux through passing through this region, electric field lines passing through this region. Yes. No idea. Okay. So now let us draw the conical figure. This would be the conical figure. Right. And this will incorporate this whole base. Is that clear, guys? Yes, guys, is that clear? Am I audible, guys? Chavez, Tarif, Madiha, Faiza, am I audible?
So,
Yes. So Madiha has just joined, guys. You guys need to reply. Okay. Tarif and Chavez. Faiza doesn't speak. I don't know why, but okay. So this would be the conical shape, right? And we need to figure out this angle, because we know that what is the solid angle? We know the solid angle is 2 pi 1 minus cos of this theta. So remember your 10th class, guys. This is the diameter. So this would be what angle? This angle would be how much? The total angle. This is 180. So remember the property of the circle. If this is the center and let's say this is the arc, so whatever is this angle is half of this angle. Let's say this is 2x, so this is x. So for this diagonal, the angle is 180. So what would be this angle? Yes, Chavez and Tariq. What is this angle? Let me draw the diagram here. This is your diagonal diameter, and this is, so this is 180. This would be how much? Yes, property of the circles, 10th class. This is 180, half of it is 90, right? So the total angle is 90, so this would be 45, 45. So now you guys know that this theta is 45. So solid angle would be 2 pi 1 minus cos 45, which is 1 by root 2. And if you know this solid angle, then you can calculate Oh, Tarif got disconnected. Then you can calculate what would be the flux. So this is Q by epsilon naught and 2 pi 1 minus 1 by root 2 and 4 pi. So this cancels and we have Q by 2 epsilon naught 1 minus 1 by root. This is the answer. Just in how many steps? 1, 2, 3, 4 steps. You got the answer. So this is how this solid angle is very important, guys. Yes, Faiza and Chavez, understood. Okay, so if you guys just you guys take the screenshot and then we'll start the new chapter. Take in the screenshot, guys. Okay, so now let us, the next chapter is electric potential. Let me write. And in the first part, I will talk about work done in external electric field. Okay, so yeah. So in your mechanics class, you guys have already done this work done. Right, whenever you apply some force and you displace some object, so there is some work done, right? Is that correct, guys? So you have yeah, you apply some force on this object, right? And this object is displaced by, let's say, this distance, right? So you apply some force, then the work done would be F dot S, right? This would be work done. Is that clear? Or let me write it as only F into S for the time being. Okay. Yeah, so this you guys already know, right? Okay, so now you can have two kind of forces. So you can have the uniform or constant force, right? Or you can have variable force, right? So for uniform force, the work done would be F dot S. And for the variable force, work done would be integral of F dot dr. Right. This you guys already know. Right, guys? Is that clear, guys? Yeah, Chavez and now Madiha, this is clear to you, right? Okay, so now what we have this force, right? And this force is produced by, so in this topic, we have work done by electric field, right? So in the previous chapter, we have learned that whenever we have some kind of electric field, right? Whenever we have some kind of electric field and we place some, let's say, charge here, right? So this will experience some force, right? This charge will experience some force and that would be equal to QE, right? In the direction of the electric field. Is that clear, guys?
Yes.
right? So then what would be the work done in the case of the external electric field? Okay, so
Can I scroll up?
oh yes, what happened? Which part? This part?
Sir, about
Yes.
sir.
Okay. So now this force, we understood that there could be two kinds of forces, but in the case of this electric potential or electric charge chapter, this force is generated by electric field. And how it is generated? In the presence of this electric field, the force would be simply QE, right? And then we are doing what? We are taking this charge, right? We are taking this charge and bringing it to the some point. Let's say that this is 1 point, right? And we are taking this charge from this point, okay, and we are taking it to be here. Okay, is that clear, guys? Right. So this is the force due to the electric field. But we are working against this electric field to bring this charge from here to here. We are working against this electric field, right? So this would be in the opposite. This would be some external force. So this would be F external, right? Because let's say that you guys have learned in your potential chapter, right? That let's say you have this source charge, right? And it has some influence. And you have this Q charge, which is at infinity. So you are bringing this charge from here to here, right? So let's say this is point P. And this Q charge is experiencing some force in this direction. And this is how much? Q by, let's say this distance is x. So x is square. And in this direction, let's say I. But to bring this charge from here to here, right? This will not come automatically because this is experiencing some force in this direction. So we have to apply some external force, right? External force in this direction to bring this charge from here to this point. So the work done would be due to this external force that we are applying. And this F external would be exactly equal to this force, electric force, but in the opposite direction. So similarly, in this case, right, we are bringing this charge from 1 to 2 point. So the work done would be how much? This would be due to the F external, right? Dot dl. Let's say this distance is dl. So dl. And we are bringing from 1 to 2. Okay, is that clear, guys? Is this clear, guys?
Yes.
So okay. So F external is how much? We are working in the presence of electric field. We know that F is QE, so F external would be minus of Q. Is this clear? This should be vector. Is this clear, guys?
Yes.
Okay, so then we can write the work done in the presence of electric field in bringing this charge from 1 to 2. This would be simply minus of QE dot dl. And this is from 1 to 2. So we can take this Q outside. So this would be E dot dl 2 to 1. Where did Tarif go? Where did Tarif go? So, yes, any doubt in this, guys? Yes. Okay. So you can see that, yeah, you can see that there can be two possibilities of electric field. Just like the case of the force, you can have two possibilities. So one would be that this electric field is uniform. So E is uniform, or E can be, or E is variable. Okay. So if E is uniform, then this work done would be simply minus of Q E dot, this is 1, so this would be R1 minus R2. Okay. Yeah, is this clear, guys?
Yes, sir.
Yeah, we can write this this one as so. Yeah, this would be. And if we have, let's say, if we have a variable force. So if we have a variable force, so this would be just in the integral form. Q1, 2, and then E dot dr. So this would be in the integral form for the variable force. And this is for the what, uniform, not force, but variable electric field. And this is uniform electric field. Yes, that's the uniform, right? Yes, that's for uniform electric field. This is for uniform electric field, and this is for the variable electric field. Just like the case of this can be also written as so this can be also written as 1, 2 would be minus Q dot, not dot, but E dot R A N R21. Okay. So we can write it in this way also. Is that clear, guys? Because R21 would be how much? So let's say this is R2, this is R1, and this is R12, right? So R12 would be how much? This would be R2 minus R1. So R21 would be how much? This would be R1 minus R2. Just remember the vector portion. So then you guys would be able to understand. Is that clear, guys? Yeah. Where did Tarif go? So where did Tarif go? Hmm. Okay, so let me do some question based on this, then you guys would be able to understand. So yeah, we have this question. Okay. So find the work done by an external agent in a slowly shifting charge Q equals to 1 microcoulomb in the electric field of how much? E equals to 10 cube I hat and a volt per meter from point P to Q, which is 3/4. Okay, this is the question. So can you guys tell me? Okay, so Chavez will tell me. What kind of electric field is this? Is this a variable electric field or is this a uniform electric field? What kind of electric field is this? Yes. Oh, so could you scroll up just a minute? Okay, okay. Sorry about that. Sorry about that. So is this okay, Faiza? Okay. Yeah, so we have this question that we have to find the work done. So we have to find the external work done in slowly shifting charge Q 1 microcoulomb in the presence of this electric field, which is 10 cube I volt per meter. So from point P to Q. So we have to find work done in moving some charge from P to Q. Right. We have to find that. So you guys tell me that, yeah, you guys tell me that, is this the uniform electric field or the variable one? We have this electric field, which is 10 cube I hat. So is this uniform or varying? Yes. Anyone? Let's say that if I write electric field as yeah, uniform, right, Madhya? Uniform. Why? Because we don't have any function of x, y, or z. If I write this as 3x square I hat plus 2x cube, 2y cube j hat plus 3xy k hat. So this electric field is varying. Right, this electric field is varying, but this electric field doesn't vary. So this is in the I direction, which means that this is only in X direction. So this is like this. Is this part clear, guys? Yeah. Okay, so we need to find out work done in moving this charge Q from P to Q. And what do we know that this PQ would be simply how much? This would be minus of QE dot RP minus RQ. Is that clear, guys? Is this clear, guys?
Yes.
Okay, so Chavez, you tell me that what is, so this is P. So what is RP? Yes. What is RP? What is the position vector of P point? Yes, guys. Travis, what is RP? Who's going to tell me? Who's volunteering to answer this question? Let's say I have this point, which is, let's say, 1, 2. So what is the position vector? How much I have moved in X direction, how much I have moved in Y direction. So what is the position vector? This would be I hat plus 2J. Right. Right, guys.
Oh, yes, yes.
And RQ would be how much?
3I cap plus 4J.
Right. So this you guys have learned already, right? So this would be QE dot RP is I plus 2J minus of 3I minus of 4J. And this is minus Q. E is how much? 10 cube I hat. Dot of I minus, so minus 2I and minus of 2J. So which term will survive? I have I dot I and J. So what would be the term that will survive? I. Oh, Tarif. Okay. Yes, Tarif. Yeah, Tarif. Hello, can you hear me?
Yes, I can hear you.
Yeah, you got disconnected.
Yes, sir.
So network issues, some.
Yes, sir.
Okay, so please, guys, give me 5 minutes so that I can repeat. Yeah, so you left at the conic portion that we were doing. So let's skip that. And I have just started this the second chapter, right? So in your laws of motion, in your 11th portion, you already know that how can we calculate the work done? So work done is just force and the displacement that the body is that body makes, right? So Fs, the work done would be Fs, and there can be two forces, uniform and variable. So for uniform force, this would be the work done, and for variable, this is the work done. So similar idea we apply for the case of the electric field also. So when you place some charge on in the electric field, so this is the electric field and you place some charge. So this will experience some force in this direction, right, Tariq? And this would be how much? Tarif. Yes. So this would be QE, right? So due to this QE, there would be some external work done, right? So in the presence of this external electric field, there would be some work done. Not the external electric field, but the presence of the electric field. So in this electric field, we are moving some charges. And if we are displacing these charges from this point to this point, so there would be some work done. And this is against this electric field, right? So then this work done would be simply this F external dot dl. And this would be simply F is minus QE, so minus QE dot dl. So this is the work done in external electric field. And this E can be uniform and variable. So for uniform case, this is the work done, and for the variable case, this is the work done. Okay, so this was the idea, and then we did this problem. So we have to find the work done, external work done in moving the charge from Q equals to 1 microcoulomb in the electric field of 10 cube I from point P to Q. So this we were calculating. Okay. Yeah, so you come again 15 minutes early in the next class, and then I will revise this for you. Okay, Tariq?
Okay.
Yeah, so so only I dot I will survive, right? So Q is 1 microcoulomb. So 1 into 10 to the power minus 6. This is 10 to the power 3. And I into minus 2I. So this would be minus 2, so plus 2. So this would be how much? 2 into 10 to the
Sir.
power minus 3, right? So this would be the
Sir.
one. Yes.
Can you scroll up? Actually, my guest came, so I couldn't.
Yeah, which portion? Which portion, Chavez? Which portion, Chavez?
Little more, can you scroll?
Your voice is breaking.
Little more, can you scroll?
Okay. This portion.
No, sir, down, sir, little down.
Yeah. Is this okay?
Yes, sir, little more down. Yes, sir, finished.
Okay, so this would be the work done for the case of the uniform electric field, right? For the uniform electric field, the work done is simply minus QE dot R1 minus R2. This is the work done. Okay. And now the next question is, so next question is about the work done.
So can you scroll?
Yeah. Oh, you guys didn't note it down. Okay. Yeah, you guys please quickly note it down. Yeah. So, sir, could you please scroll up? Okay. So where should I scroll it up more, Faiza? Okay. So whenever you guys find out that this kind of electric field is given, just apply this formula. Whenever you guys have finished noting, please tell me. Yeah, done, everybody. Okay, Faz has noted. What about the rest of you guys? Yes. Chavez, Tarif, Madia, done.
Yes, sir.
Yes, sir.
Okay, so the next question is about work done in the presence of variable electric field. Okay, so in the presence of variable electric field, how do we calculate the work done? This is 1 2 minus q e dot dl. Right, guys? So if this is called the length element, and if we are moving in 2 dimension, so dl would be dxi plus dyj. Just remember this. Okay, whenever we are moving in 2 dimension, so this would be dx, and this would be dy.
Explain this again.
Yeah, so whenever we are moving in 2 dimension, okay, so there will be two elements. So let's say that let's say we are moving like this. Okay, we are moving in this way and this way. So this is dx, and this would be dy, your line
Sir, the
variance.
charge is moving.
No, charge is not. Yeah, we are bringing this charge from, let's say, here to here. So from this point to this point, we are bringing. Okay, is that clear? So this would be dl.
Yes, sir.
Okay, so if we are in 3 dimension, this would be dz and k hat and so on. So yeah, so just remember that for the case of the variable electric field, this would be the work done. Okay, now let us solve one question. So we have this charge, right? So this is point O, let's say, and we move to point P, and then we move to point, let's say, Q, and then we come back to this point. So this one, and this one. And this point is obviously 0 0. This point is 2 0, and this point is let's say 2 2. Okay, so you guys tell me that what would be, and the charge that we have to bring. So let's say that I am moving a q charge, which is minus 10 microcoulomb. So I have this charge q, I am moving, right? So first in this direction, then in this direction, and then in this direction. Okay, so yeah, and the electric field is like this. So what kind of electric field is this? Uniform or variable?
Variable.
Variable, right? So we have to question is that we have to calculate
So what is x here?
x. So x is the variable, right? Your electric field is dependent upon two variables, x and y. So is that clear?
Yes, sir.
Yeah. So we have to calculate the work done from O to P, and we have to calculate the work done from P to Q, and then what is Q to O. And then we have to calculate the total work done. So this is the question. Is that clear, guys?
Yes, sir.
Okay, so from O to P, my length element would be in which direction? So how many direction do I have? From O to P. Yes, from O to P, if I write DL, because I am moving in this direction only, right? So DL will have dxi, dyj, which part will not be there? Yes,
Y part.
yes, y part will not be there. So DL would only be dx I hat. Is this clear, guys?
Yes, sir. This is from second chapter.
Yeah, this is from second chapter, right? We are in the potential, right?
Today only we started, right?
Yeah, today only we started. Yeah, so you were there in the previous class, right? So in the previous class, we did this electric cavity problem and that solid angle problem. So after that, yeah, this is the chapter. Okay. Yeah. So any doubt in this, guys? Okay. So now what would be the work done from O to P? So this would be simply minus of Q. And what would be the points? So let's say this is so you see here that this is 1 and this is 1. So this is from O to P. Okay. And E dot dx I get. Okay. Is this clear, guys?
Yes, sir.
Yes.
Okay, so this would be minus of O to P, and Q we can take outside. E is how much? X plus 2y and I. And let me write only the I part, because J part will cancel out, right? J dot I would be 0. So only the I dot I will serve. Okay, let me write that, and then let me first write that and dot dxi. Okay, so I and I will survive, and I will get how much? Q O to P x plus 2y, right, and dx. So this is the final integral that I have. Is that clear?
Sir, we have to find work done from all points.
Yeah, first we have to find from O to P, then P to Q, and then Q to O, and then total work done. Okay.
Hmm.
Okay, so and you guys tell me that in this direction, y is what?
It's null.
This y is 0. So this part cancels out, and I have only this integral. So Q and O to P. So dx is the integral that we are taking with respect to. So what would be the limit here? What would be the limit? The limit of x, the limit of y, or limit of z? What would be the limit? Yes,
X.
x. So x is going from 0 to 2. So this would be 0 to 2, right? And x dx. So this would be minus, and this is minus 10 into 10 to the power minus 6. And x integral is x squared by
Can
2.
you just explain how did we take 0 to 2?
Yeah. So we are going from O to P, right? So O is 0, comma 0. P is what? P is 2, comma 0. Right. Is that clear,
Yes,
Charles?
yes.
So we are taking the dx, we are taking the integral with respect to dx. So we will take the limit of which part?
X part.
X part only, right? So that is why 0 to 2. Understood?
Yes, sir.
Okay, so this would be how much? This would be minus minus plus, so 10 into 10 to the power minus 6, x square by 2. So 2 to 0, so this is 2 square by 2. Or this guy comes over here, so 4. So this cancels, and we have 2 into 10 to the power minus 5 joules. Okay, this is the work done from O to P. Is this part clear?
Yes, sir.
Okay, so you guys note up to this point, and then we'll go ahead, because yeah, I tend to forget that you guys have not noted it down, and then I go ahead. So you guys first note down this problem, and then we'll go ahead. Yeah, so we are understanding about the work done in the electric field. And then we will relate this electric field to the electric potential. So this is the idea. Because work done is related with potential. So, and work done is related with electric field. So we can relate electric field to the potential. Yes, noted, everybody.
Yes, sir.
Okay, so note up to this point. Yeah, done, guys.
Yes.
Okay, so let me solve it here.
No, sir. Can you just
Oh, sorry about that.
yes, sir.
Yes, Tarif and Feza, noted.
Yes, sir.
Okay, so now let us calculate the work done in going from P to Q. So P to Q. This would be how much? Minus of Q, and this is P, and this is Q, and E dot DL. So you guys tell me that what would be DL in case of, so in the case of this point, DL would be what? We are moving in one direction only. So this would be, yes, guys. This would be dx or dy. Which part will survive? Which part is 0? Dy. Yes, yes, right, Faisal. So good, dyj. So this would be the line element, right? So we plug in the values in here. So this would be Q, P to Q, and E is how much? X plus 2y I plus 2xj and dot dyj. So only j and j will survive. So we will have, again, this part will cancel out, and this is pq, this is 2x dy. Is that clear, guys? Yes. Okay, so now this is in the form of dx, right? And this is dy. So what is the function? Is x varying here? Is x varying in this case? Yes, guys, is x varying in this case? Yes, guys, x is varying or not in this case?
Yes.
X is fixed, right? X is not varying. Okay. So we can take it, right? So in this case, what we did, x is how much? X is 2 here. Right, so x is 2, we can plug in the value, this would be q, and this is 2, so this would be 4, and only the integral of dy, right, pq. So dy integral is y, right? So this is q into 4, and this is y, right? So y, and the limit would be how much? So this would be, limit is 0 to 2. So this is 2 to 0, right? So this would be 2. So this would be minus of q into 8. So minus 10 into 10 to the power minus, oh, there was minus 1 also. So minus 6 and 8. So minus of 80 into 10 to the power 6. So 8 into 10 to the power minus 5. Is this clear, guys? Is this clear?
Yes, sir.
Yeah, did you guys understand
Sir,
that?
minus 10 into 10 raised to minus 6.
Yeah, did you? Yeah, so I'm asking about this part.
Yes, sir.
Yeah, so you see that what is the x value here? What is x here? Right, x is 2 only. Right, Tarif? X
Yes,
is
sir.
2. And it is not varying, so we can take it outside. So 2 into 2, 4 outside. And we can take the integral of dy. So integral of dy would be y, and then we put the value of y limit. So this is how we get this. So you guys note it down, and then we will find the final work done from Q to O. Okay. Yeah. Whenever you guys have finished noting, please tell. Yes, done everybody.
Sir.
Yeah. Okay, so yes, let me erase this part. Tarif, Madiha, Faiza, done.
Yes, sir.
Okay, so let me erase this part and okay, now let us calculate the final one. So just remember that this is 8 into 10 to the power minus 5. Okay, so this is Q to O. So this would be minus Q to O E dot dl. And you guys can see that in this direction, we are moving in both the X direction and the Y direction. Right. So we have two direction in here. Is that
Yes, sir.
so dl would be dxi plus dyj. So let us plug in these values, and we have minus q, and this is O, and E is how much? X plus 2y I hat plus 2x j hat, and dot dxi plus dyj. So I will survive, right? So minus q dx, so this would be q to O x plus 2y dx, and plus q to O 2x dy. Okay, so is this clear, guys? Yes.
Sir.
Okay, so you guys see that we have the integral with respect to x in here, but we have this function y. So we have to figure out how to remove or how to replace this y part. Right, so can you guys give me, yeah.
You can just explain how did we get two integral like O to Q two times?
Yeah, so x plus y I dot dxi. Right, so I will survive. I dot I will survive. So I is x plus 2y dx. This part is I part. And this is j dot j will survive. I dot j will be 0, j dot I will be 0. So 2x dy. Is this clear?
Yes, yes.
Okay, so yeah, I was asking that how can we remove this y from here? Yes, guys. How can we remove this portion?
Repeat the question, sir.
Yeah, so you see that this integral is with respect to x, but we have this y here. So I cannot integrate y as dx until I know that I can write y as some function of x. So I cannot integrate this, right? Can you integrate y dx?
No, sir.
We can integrate only x square dx, x square something or something function of x. So can you guys find out or think that how can we replace this y from here? Just look at this diagram and tell me how can we, yes, tell me how can we get rid of this y?
Can we take y as common?
Why common?
Yes, sir.
No, Tarif, you see that y is some function. This is not a constant. So if this is some function that we cannot take it out of the integral, right?
Right.
So can you divide
By dividing with what?
dx and dy?
Okay, so let us not let me give you guys some hint. So you have this x, you have this y. So I have this diagram. So how can I write this line? Yeah, this line is represented by how?
Y is equal to mx.
Angle is 45 degree. So you see 0022. Yes, you are right, y is equals to mx, but for this case, y would be, again, let me give you one more hint. So this is 0, 0, this is 1, 1, this is 2, 2. So tell me. Yes, you are close, Chavez. You are close. Yeah, so if my slope is, so you see that 0 is 0, 1, 1, 2, 2. So y is equals to x, right? Is that clear, guys?
Can you just say once?
Yeah. So you see that this line is 0, 0, 2, 2. So your x equals to y here, x equals to y here. So this line represents a straight line where your x is equals to y. So this is represented by y equals to x, right?
Okay, yes, sir.
Yeah. So anybody else got any doubt? Is this clear, guys? Yes.
Yes, sir. Yes, sir.
Okay. So now we can write this QOX plus 2x dx, and this we can write as so this is in the form of y, so we can write this as 2y dy. So we can write this as this integral is 0, not 0, 2 to 0, x plus 2x, which is 3x, dx plus 2 to 0, 2x dx, dy, 2y dy. Okay. Yeah, so we can write this as y. Yeah, we can write. Okay, so is this clear, guys? So this integral would be how much? Minus q, and this is 3x. So 3 is outside. This is x square by 2. Right. So this would be 0 to 2. And this is 2 outside, y square by 2. And again 0 to 2. So this would be how much? Minus q 3 by 2 into, this is minus 4. Right, so this is minus 2. And this is how much? So this is 2 cancels, right? And we have minus 2. Minus 2 again. Right, so 2 cancel, I have 4, not minus 2. Is that clear, guys?
Yes, sir.
Okay, so this would be how much? So this would be minus of minus 10, and 10 to the power minus 6. And this is minus 6, and this is minus 4. Right, so this is minus 10. Okay. So this minus minus cancels. I have 10 to the power minus 5 into 10. Minus 10. So minus 10 into 10 to the power minus 5 joules. This is my work done from Q to O. Is this clear, guys?
Yes, sir.
Okay, so please note it down. Please note it down. And yeah, so do you guys remember how much we got for the work done for the point P to Q? It was 8 into 10 to the power minus 5 joule, right?
Yes, sir.
Yeah, so please you guys note it down, and then we will try to solve the next one. Yeah, whenever you guys need me to scroll down the screen, please tell me. So oh, who got disconnected? Yeah, done, guys.
Yes, sir.
What about rest of you guys? Done.
Thanks.
Yeah, did you guys understood about this limit? So I took 2 to 0, right? So 2 to 0. I was going from Q to 0. That's why 2 to 0. X is going 2 to 0, Y is going 2 to 0. So that is why 2 to 0. Yeah, you guys quickly note it down, and then we'll talk about the total work done.
So the total work done will be the scalar sum, right?
Yes, of course, the scalar sum, because the work done is a scalar quantity. So algebraic sum, scalar sum.
Yes.
Done. Okay, yeah, noted everybody, noted up to this point. Yes. Tarif, Madiha, Chavez.
Yes, sir.
Oh,
Noted.
Yes, sir.
okay. Okay, so now let me write this in here. So we calculated that. So we had this OPQ point, and we calculated in from going here to here. WOP was 2 into 10 to the power minus 5 J. And from here to here, we got WPQ. This was 8 into 10 to the power minus 5 J. Am I writing it correct? So you guys please check and tell me if I'm writing it correct. And then in here to here, I calculated Q to O. This was minus 10 into 10 to the power. So are these numbers correct, guys?
Yes, sir.
Okay, so the total work done would be how much? The algebraic sum, as Chavez said. So WOP plus WPQ plus WQO. So this is 2 into 10 to the power minus 5 plus 8 into 10 to the power minus 5 minus 10 into 10 to the power minus 5. So this is 10 into 10 to the power minus 5 minus 10 into 10 to the power minus 5. This cancels and we have 0. So you see that the work done in the closed path, is 0. Okay, who left? Yeah, Chavez got disconnected. So work done in the closed path is 0, which means that the electric field or the force is what? Right, guys? For the conservative force, the total work done in the closed path is 0. Is that clear, guys? Yes. Yes, guys. Any doubt in this? Okay, so you guys please note it down, and because Chavez got disconnected, so we will not go ahead. So in this part, we learned that how work done is related with electric field. So in the second part, we will learn that you guys already know that the work done or the potential is defined. So this is work done in bringing a charge from infinity to a fixed point, and this is the potential. Right, guys? So then in the next part, I will relate this potential with the electric field. This would be my idea for the next class. Okay, guys. So yeah, see you guys.